Kinetics 2, the collision theory for rates of reaction. A chemical reaction occurs only when reacting molecules collide successfully. For example, when you want to react hydrogen with chlorine to get hydrochloric acid, the hydrogen molecule and the chlorine molecule must collide in a certain way. So the reactants smash into each other. If it's a successful collision, the reaction takes place and you get the products. The rate of reaction is the number of successful collisions divided by time, or the frequency of successful collisions. So what makes a collision successful or effective? Two things are required. Firstly, the reactants collide with reactants collide with sufficient kinetic energy. Energy is needed to break reactant bonds and to overcome electron cloud repulsion of approaching molecules when reactants change the products. The minimum energy needed to convert the reactants to the products is known as the activation energy. This energy is provided by the kinetic energy of the reacting molecules. Secondly, the reactants must collide with the correct geometry or orientation. And if we look at that example we just talked about with hydrogen and chlorine gas, if the hydrogen and chlorine gas are aligned like so, then this is the correct collision geometry for a reaction to take place. If they were to smack into each other head on like this or like this, then no reaction would take place, no matter how much kinetic energy was involved. So activation energy. This is the minimum energy needed to convert the reactants into products. And a good analogy of this is if you think about a hill on a cycling route, which is just like activation energy. The cyclist comes along, and if he wants to get to his destination, which is down here, he first must build up enough kinetic energy to get up and over the hill before he can go down to his destination. In the same way, reactants must have sufficient kinetic energy to get up and over the activation energy before they can form their products. If you have enough kinetic energy, you will get to the top of the hill and turn into products. If you don't have enough kinetic energy and no products will form. It'll be an unsuccessful collision. And this is a potential energy graph and it shows activation energy. So if we've got reactants and they smash into each other with sufficient kinetic energy and the correct orientation, you make an activated complex. The energy or kinetic energy required to form this activated complex is the activation energy here. So you can see reactants, the potential energy of the reactants, and the energy of the activated complex is a lot higher. And then in this case, the product's energy is down here. So the activation energy is just the energy added to break reactant bonds and overcome forces of repulsion between electron clouds as molecules approach each other. It's worth memorizing that. The activated complex is a high energy unstable transition state that forms when the reactants collide successfully with the correct geometry and sufficient kinetic energy. Once the activated complex forms, the reaction proceeds to form the products. The rate of reaction depends on the activation energy. Reactions with lower activation energy are fast, and you can see obviously there's less, the kinetic energy required to overcome the activation energy is smaller. Here, reactions with higher activation energy, more energy is required for sufficient energy, more energy is required for successful collisions, so it's going to be a lot slower. We use something called the Maxwell-Boltzmann diagrams in collision theory. Maxwell-Boltzmann diagrams show the number of or frequency of molecules with a given kinetic energy. So over here you've got the number of particles So here you've got very few particles, here you've got lots of particles, over here you've got very few particles. And along the x-axis you've got kinetic energy. So these are particles with high kinetic energy, particles with very low kinetic energy, particles in the middle here. Okay. The area under the curve represents the total number of particles in the sample, which is fairly straightforward because if you had like do them all as lines, you would have and counted them all up, you would get the total number of particles. The effect of high activation energy on the rate. So high activation energy means a slow reaction. Let's have a look. If you've got the kinetic energy here, next axis, and we just say this is where the activation energy is. This is the minimum kinetic energy needed for reactant molecules to successfully collide and form an activated molecule complex. In that case, only things to the right with kinetic energy above this level will collide successfully. And you can see here this smaller area represents the number of molecules with sufficient kinetic energy to overcome the energy of activation. So the number of molecules that collide successfully is low here. But you can see here that a whole bunch of molecules, this entire area, this area represents the number of molecules without sufficient kinetic energy because they're all below the activation energy. And so the number of molecules that do not collide successfully is high because it's all of these. Okay, let's look at the effects of low activation energy on rate. So low activation energy will have a fast reaction. If we look at our Maxwell-Boltzmann diagram here, you can see, oops, we'll put in the activation energy level. It's far lower. Okay, we've got a low activation energy, which means that far more of the particles now will be found with kinetic energies above that energy level. So this larger area represents the number of molecules with sufficient kinetic energy to overcome the energy of activation. And so the number of molecules that collide will be higher. This smaller area represents the number of molecules without sufficient kinetic energy to overcome the energy of activation. So the number of molecules that do not collide successfully will be low. Here are the 6 factors that affect the rate of reaction. 1, reactant concentration. 2, pressure, that's for gases only, and it's really the same as concentration. 3, particle size and surface area. This is only for heterogeneous reactions, for example, when a liquid and a solid react. 4, temperature. 5, catalyst. 6, nature of reactants. And this is due to the effect of activation energy. So, how can we change the rate of reaction? Well, the rate of reaction is proportional to the frequency of successful collisions. So that's the number of successful collisions in a given time. Another way of thinking about that would be that it's the total number of collisions multiplied by the fraction of successful collisions divided by time. So, for example here, let's have a look at that. If you've got 400 successful collisions in a given time, but there's a total number of collisions of 1000, you're going to have a fraction of 0.4. Similarly, if you have 1000 here, but 600 were successful, then you're going to have a higher fraction of success. Let's look at the effect of reactant concentration. Here you can see a few molecules crashing into each other, and there's not as many here to crash into each other. So there's fewer collisions. Here, they all squish together at higher concentration, so they're going to hit each other more often. There'll be more collisions. So an increase in reactant concentration equals an increase in total number of collisions. Therefore, you're going to get more successful collisions per unit time. So reaction, why does the rate of reaction decrease over time though? It's to do with concentration. As reactant concentration decreases, you get fewer total collisions. As you get fewer total collisions, you get fewer successful collisions per unit time. So here, you've got, say, a concentration of 0.005. They'll be hitting each other, the reactant particles will be hitting each other far more often than over here when you've only got 0.001 moles per decimeter cubed of the reactants. And so the rate of reaction here is going to be far quicker. You can see the slope is steeper than down here. The effective pressure change, it obviously applies only to gaseous systems. When pressure increases when volume decreases. And you can consider this just to be the same as concentration. You can see here this wonderful diagram. The molecules are all spread out, so they're not hitting each other very often. As you push the plunger in, they get squished together. And so they do start to collide with each other more often. At higher pressures, a greater number of total collisions, therefore a greater number of successful collisions per unit time. Factors affecting the rates of reactions. This one we're going to look at is the effect of surface area and particle size. And this is only for heterogeneous reactions only. So mainly with solids here. So you've got a big lump. Say if you've got a clump of reactant here and little particles of reactants here in blue. So here we've got a low surface area in the, when it's a large particle size, all these little atoms are making up one particle. Then you're going to get fewer total collisions between the reactants because the red reactant, the red particle reactant, will not hit the blue, let's say, molecules or atoms of this big clump as often. There'll be fewer successful collisions per unit time. Conversely, over here, the red particles have better access and can hit more of these blue atoms and molecules here. And so, the smaller particle size leads to more total collisions between reactants and more successful collisions per unit time. If you look at here, I know it's a bit small, you can see we've got total amount of product made on the left. So we're looking at product made against time. If you've got a greater surface area, say if you're using a powder instead of a lumpy material, then you're going to get a faster reaction. It's steeper because more collisions can take place than if you've got lumps. Okay, how does temperature affect the rate of reaction? We've got a Maxwell-Boltzmann graph here. So we've got a number of particles on the left, we've got kinetic energy here. What high temperature does is it moves the line, or the graph line, further to the right. So instead of having, if this is the maximum number of particles with kinetic energy, remember kinetic energy is tied to temperature, kinetic energy being a measure of, temperature being a measure of kinetic energy, you can see that we're just pushing it along. We're getting far more particles with increased temperature and with high kinetic energy. So obviously, even though the activation energy stays where it is, we're just going to get more particles here. So at the low temperature, this lower temperature line here, you can see the small area which shows fewer molecules with sufficient kinetic energy to collide successfully. There's very few particles here. But at the higher temperature, the larger area shows more molecules with sufficient kinetic energy to collide successfully. Therefore, we get higher frequency of successful collisions. The temperature change affects the total number of collisions. This is kind of obvious. If the molecules or particles are just moving around quicker, they're going to hit each other more often. Secondly, the fraction of successful collisions will be higher too. So they're hitting each other more often, and when they do hit each other, more of these collisions are successful. You get a larger shade under the graph because of the fraction of successful collisions, and you're getting hitting each other more often. It's the fraction of successful collisions which is more important. A general rule of thumb with temperature is that a 10 degree Celsius increase in temperature will double the rate of a reaction. Effective catalysts. What is a catalyst first of all? It's a chemical species which increases the rate of a reaction without being consumed in the reaction. It's regenerated at the end of the reaction and can be reused, and it provides an alternate reaction mechanism with a lower activation energy. So let's look at this potential energy diagram. We've got the reactions going to the products, and so you see obviously the enthalpy change doesn't make any difference. You're going to have the same enthalpy change with the reaction, but the activation energy does change. This is it without a catalyst. You see it's higher, and if you use a catalyst, an alternative mechanism is available, it lowers the activation energy, so the rate of reaction will increase. If we look at it on a Maxwell-Boltzmann diagram, what a catalyst does is actually shifts the activation energy further down. It requires lower kinetic energy to overcome it, so you end up with far more particles having successful collisions because they've got sufficient kinetic energy to overcome the activation energy. Conversely, you're still going to get some not conversely. An activation energy without a catalyst here, you're going to get fewer particles with sufficient kinetic energy to overcome the activation energy and have successful collisions. Let's have a look at an example. The catalysis of hydrogen and oxygen using a heterogeneous platinum catalyst. We've got oxygen in blue here. No, sorry, that's not oxygen, that's hydrogen in blue. We've got oxygen in red. It moves over to the platinum surface where it gets adsorbed on the surface. This weakens or stretches the oxygen bond, which weakens it, and then the hydrogen can then come in, react with the oxygen, and form a water molecule. Notice it says adsorbed, not absorbed. That means it's on the surface. Okay, let's consider an empty soda bottle filled with air. The air is mostly nitrogen gas and oxygen gas. So there is a potential for this reaction to take place. At room temperature, mathematical models show that there are approximately 10 to the 30 collisions per second between nitrogen and oxygen. So you'd expect a lot of reactions to take place. However, less than 1 in a million collisions are successful and actually provide nitrogen monoxide. I'd like you to go away and find out why that is. And that's the end of this presentation. Splendid.